Okay, I've added a little more to this problem. I wanted to give it some initial conditions. There were 21,792 people in this town we're looking at in the year 1990 and 24,315 in the year 2000. So using this model, how many people would you expect there would be in the year 2012? Alright, so I'm going to have to do some erasing here to make room here, but now we've taken this differential equation, we have a general solution that describes population growth or decay, and now I'm going to solve a specific problem with these initial conditions. And let's see here, in 1990, let's call that t equals to 0. So in other words, the initial population, P0, sometimes we call this P naught. Naught is spelled N-A-U-G-H-T. It's an archaic form of nothing or nil. Initial population P naught was 21,792. So that solves this part of this problem. That means my population is 21,792 e to the kt. And now to solve for k, I need this information. So year 2000 is what? It's t equal to 10. It's 10 years later. So p at 10 would be 21,792 e to the 10k. So replace t with 10k, equals to this number, 24,315. So, see what I mean? I have to do a lot of erasing on this little board to fit these problems in. Now then, to solve this problem, and I also wanted to go through this problem, just kind of review solving exponential type equations, because we'll use logarithms a lot this quarter, exponential functions a lot. And so this is also a good kind of review in case you need it. Right, to solve for k, I'm solving for k, my growth constant. I need to divide both first by 21,792. So e to the 10k is 24,315 divided by 21,792. And to get k out of here, I have to reverse the exponential function. I have to take its logarithm. So I'm going to take the natural log of e to the 10k equals to the natural log, parentheses, 24,315 over 21,792. Natural log will cancel the e, leaving 10k. So 10k equals this number, which means that k is equal to the natural log of 24,315 over 21,792, and all this is divided by 10. So let's run that through a calculator, see what we get. Natural log, parentheses, 24,315 divided by 21,792, close parentheses, then divided by 10, and I get 0.01096. Okay, that's 955. I find that in these problems, it's typically you want 4 significant places in order to get pretty good accuracy. You know, if I rounded off this to 0.01, you would lose a lot of accuracy, it turns out. So let's go with 4 significant places here, and we'll get a pretty good estimate, as it turns out. Much more accuracy. Alright, so now, this was k, so I can now rewrite my growth function for this particular problem. Alright, it's going to be, let's see, what will it be? P of t is 21,792 times e to the 0.01096 times t. Great. Now, what is then the population in the year 2012? So I've solved the equation, the function that describes this problem for this town, describes the growth of the population of this town under a simple assumption about how the population is going to grow. And now we can project into the year 2012. And what is 2012? That's going to be t equals to 22. So P of 22 will be 21,792 e to the 0.01096 times 22. But I tell you what I'm doing. I still have this number with all its decimal places on my calculator. So when you have all those decimal places, I want to make sure I store it, use them. So I'm not just using 1096, I'm using all the decimal places. And I'll multiply that times 22, and I'll take e to that power, and then I'm going to multiply it by 21,792. So I get the most accurate answer I can get. It's approximately 27,731. So that's our projection for the year 2012 for this problem. Now, one thing that's missing is the answer. If you have me as your professor, then I'm going to expect to word problems like this, to applications, I'm going to expect a sentence answer, because I'm big on communication. So let's write it out as a sentence. We project that there will be 27,731 people in 2012. There we go. So now it's complete. Okay, so that's probably about the simplest full application of a separable differential equation. I'm going to do another application of a separable differential equation here with the next video, which I think is you may not have seen, but could be pretty interesting.